Hello, welcome to another Physicsmeister video. In this video, we're going to talk some more about the relationship between electric fields and magnetic fields. Now, you've already learned that a moving electric charge can cause a magnetic field to occur. I hope you've learned that. If you haven't, you probably should do that first. But in this video, we're going to kind of look at the opposite situation. What happens when you have a magnetic field, in particular, a magnetic field that is changing, or to be more precise, a magnetic flux that is changing. We'll talk about that because we're going to find out that a change in magnetic flux can cause an EMF. In other words, an electric field that would cause a voltage to occur in a situation that would cause charges to move if there were charges present. Before we begin, you probably should familiarize yourself with the phenomenon that we're talking about here. Basically, what we're talking about is, let's say you have a coil of wire like in this picture here, and you have a magnet, and you bring the magnet so that the north end of the magnet, let us say, points towards the center of that coil of wire, and you bring the magnet closer to that coil. What happens to the current flowing in that coil? If you hook up that coil, the ends of the coil to a galvanometer, a current meter, and it would tell you if there's current flowing or not. And then you could change things around. You could pull the magnet away. You could have the south pole of the magnet going towards the coil of wire, or going away from the coil of wire. Um, the phenomenon, you can find videos about it on the internet. They'll show you a demonstration of this principle. Um, it's usually called magnetic induction or Faraday's law. And if you look at an experiment involving Faraday's law on the internet, you should be able to find some videos about that. Take a look at one of those before you continue on with this video, so you'll have a better idea of what we're talking about once we do discuss it. So the principle we're going to examine here is called Faraday's law, named after Michael Faraday, who discovered the basic principles. In order to understand Faraday's law, we first have to review the definition of flux. In this case, we're going to be talking about magnetic flux. You may recall that in the video I made reference to the concept of magnetic flux. The concept of magnetic flux is very similar to the concept of electric flux that we studied in learning about Gauss's law. So here we're going to define the magnetic flux as how much magnetic field flows through a given area. And the symbol for flux is phi, just like it was for electric flux, but we're going to use an M subscript. The mathematical definition of magnetic flux is very similar to what it was when we talked about electric flux. If you have a field that is constant over a given area, A, then your magnetic flux is just the dot product of those two vectors. Remember, the direction of an area vector is the direction of its normal line. So then the magnetic flux would be the magnitude of the area times the magnitude of the magnetic field times the cosine of the angle between those two. Now, if your magnetic field varies over an area, we're going to have to take an integral. So we'll take the integral of b dot n hat, that's the n unit vector. Basically, it just gives a direction to the little piece of the area, dA. Now, very often in our study of magnetic flux, we're going to be concerned with how much flux penetrates the area surrounded by a coil of wire. And so a coil of wire has more than just one area that the magnetic field goes through. So the magnetic flux through a coil of loops of wire is just a magnetic flux of each loop multiplied by how many loops you have. So something like this. Let's go ahead and do a practice here. Let us say that we have a uniform magnetic field of 2,000 Gauss. Remember, a Gauss is 1/10,000th of a Tesla. And that is parallel to the x-axis. And we have a square of 5 centimeters on a side, and has just one turn, so we don't have to worry about multiple loops here. And it makes an angle of theta with the z-axis. Now let's look at this. That's very conveniently defined for us because the angle that the plane of the loop makes with the z-axis is also the angle that the
normal line to the plane, which is the angle we have to use in calculating the flux, makes with the x-axis, which is the direction of the magnetic field. So we can go ahead and use those angles just as they're given, and we can use the cosine of those angles. For example, the first one would be, it would be 0.05 meters, square that, and it gives you the area, times the magnetic field. So move your decimal point 4 places, and that's going to be 0.2 Tesla. And then times the cosine of 0, because your field is going straight through your loop there, and the cosine of 0 is 1. Let's go ahead and figure it out for that. Finish the calculation, then figure it out for 30, 60, and 90 degrees.
So here's a situation where we have to calculate the magnetic flux due to a current flowing in a long straight wire. So we have the situation is our area that we care about is this loop with a width of W and a length of L, and underneath that loop, but in the same plane as the area of the loop, is a long straight wire carrying a current I. First, let's see that there is a flux in this wire loop here, in this loop of width W and length L. If you remember how you determine the direction of the magnetic field produced by a long straight wire, you can use your right hand and have your right thumb pointing the direction of the current. So like your thumb kind of points along the wire, and then the curl of your fingers shows how the magnetic field that is produced by that wire kind of wraps around that wire. So as you can see here in this situation, since our fingers are kind of coming out of the plane of the board, we must have a magnetic field that is coming out of this plane. But the thing is, the magnetic field is getting weaker the farther away you get from the wire. And in fact, the magnetic field produced by a long straight wire is equal to mu naught times I, where I is the current, mu naught is a constant of nature, divided by 2 pi times r, where r is the distance from the wire to where you're trying to measure that magnetic field. So it gets weaker here, and what I've done is I've drawn fewer dots to kind of show you that it's getting weaker. So what we're going to have to do is we're going to have to figure out the flux caused on a thin strip of my area here. Let us say I have a strip right here, and it's just some distance from my wire. Let's call the distance that it is from my wire, let's call that x. And so therefore the magnetic field there would be mu naught I divided by 2 pi x, if you will. And then the width of my little strip, well, a little piece of the direction x is just going to be called dx. And so the area of my strip would be equal to, well, the length of my strip, which is L, times the width of my little strip, which is dx. And so therefore, the total flux is going to be the integral of the flux through each little piece that is a width dx. So that's going to be, unfortunately, the field is perpendicular to the plane, or parallel to the normal line of the plane, so therefore it's just going to be the field times the area. So the field is going to be mu naught I over 2 pi x. That's the magnetic field times the area, which is just L, which is a constant, times dx. And x is going to go from A, it's the distance A at the bottom side is the distance A from the wire. So it's going to go from A to W plus A. So I'll leave it as the exercise to the viewer as to figuring out what the actual flux is there using that mathematics and that definition. So in your study of circuits, you would have learned about this idea that the electric field is a conservative field. That means, say, when you were studying what happens to the potential of a charge as it goes through a circuit, you know that if, say, a battery causes the potential to be increased, and then as you go through the circuit, you're going to gain potential energy going through the battery, but then you're going to lose potential energy going through the resistor, let us say, so that you end up back at the same potential energy or same potential as where you started. We call that Kirchhoff's loop rule. That is because the electric field is a conservative force. But we're going to see a situation here in which it appears that it's not conservative. If there's a magnetic field present, and if that magnetic field or the magnetic flux is changing, we're going to see that an EMF can be produced around a closed loop. An EMF just means a voltage. And so we're going to have a situation where if we take a EMF, that is to say, we take the change in potential around a closed loop, we're going to find it not being equal to zero. Now, the way we say that with calculus symbols is we're going to say the EMF is equal to the integral around a closed loop. That's why we have a little circle on our integral sign, times the electric field dotted with the segment of the loop that you're going around. If the displacement times the electric field should give us a potential. So if there was just electric fields here, no magnetic fields to concern with, this would add up to zero because the electric field is conservative. But it's not going to add up to zero if there is a changing magnetic flux present. So that's what we mean when we say there's going to be an EMF produced. And so now we have all the information we need to actually say Faraday's law.
So now we are ready to introduce the actual concept that we were leading up to here. Since we defined the EMFs produced by changing magnetic fields, and we've introduced the concept of magnetic flux, we are now ready to talk about Faraday's law, which relates those two things. A change in the magnetic flux flowing through a wire loop will produce an EMF in the loop. And we write that like this. The rate of change, being given by the derivative, is equal to the EMF that's produced. The negative sign is there to tell us which way the EMF produced would cause a current to flow. And we're going to find out that the current that flows is going to oppose the change in the magnetic field. Let's do this practice here. We have a uniform magnetic field of strength B established perpendicular to the plane of a loop of radius 5 centimeters and a resistance of 0.4 ohms. The magnitude of B is increasing at a rate of 40 milliteslas per second. Find the induced EMF in the loop, the induced current in the loop, and the rate of Joule heating in the loop. A couple of things. First of all, make sure that when you're finding your area to get your magnetic flux, you are taking centimeters and converting them to meters. And then this is a circular loop, so you'll have to use the formula for the area of a circle to find the area. And then if you multiply that area times the rate of change of the magnetic field, you should get the rate of change of the magnetic flux. And so that's going to be equal to your EMF. That's essentially going to be your voltage. You take that voltage then and divide it by the resistance, and that should give you the current in the loop. And once you know the current and the resistance, you can get the rate of Joule heating. Boy, what does that mean? They're talking about the power. So you can figure out the power from that. So go ahead and work on this one on your own, and then you can restart the rest of the video after you're done.
In order to understand what we mean by Lenz's law that gives the direction of the current that gets induced, we're going to have to remember the way that a current can produce a magnetic field, in particular when a current flows in a current loop. So this is another version of the right-hand rule. If you have a little loop right here, and I just took some wire and stuck it together in a little loop. If, let us say that there is current flowing in that loop that is going counterclockwise as seen from above here. Well, then if we take our right hand and we allow our fingers to curl in that kind of counterclockwise direction, you'll notice that the magnetic field, as indicated by the direction of the thumb, points upwards, so away from that counterclockwise current there. So that's how you use the right-hand rule to determine the direction that the current is flowing in a loop, either clockwise or counterclockwise. So with that said, now we are ready to talk about Lenz's law. And I'm going to use this slide here, the situation going on in this slide, to help explain that. Let's look at the situation all the way over on the left. We have the north side of a magnet, and it is being pushed upwards so that it is getting closer to the current loop then, or the loop that can have a current flowing in it. So the first question we have to ask ourselves is, which way is the existing magnetic field pointing? Now, magnetic fields point away from north, so the magnetic field that is going through this loop of wire is going up. So the existing field is going up. The second question we ask ourselves is, what is happening to the flux? Now, the flux is just a constant area, the area of that loop, times the strength of the magnetic field, but the closer the magnet gets to that loop, the stronger the magnetic field gets. And so right here, our magnetic field is increasing, which means our magnetic flux is increasing. So the first question we asked is, which way is the current existing field going? And it's up. Second question is, what is happening to the strength of that field, or the flux that it produces? And that's increasing. So Lenz's law says that an EMF will be induced in such a way as to produce a magnetic field that opposes the change, okay? So the induced magnetic field is going to oppose the change. Now the change here is the magnetic field that is currently going up is increasing. And so Lenz's law says that the induced magnetic field should oppose that change. So how do you oppose an upwards field that is increasing? You create a downwards pointing field. So we know that we need to have a magnetic field that points downwards. And how are we going to have that? Well, as you can see from this little drawing right here, if you point your hand downwards and you see how your fingers curl, a moment ago we said the direction of the thumb is the direction of the magnetic field produced by a current flowing in a current loop, and then the direction of your other fingers are the direction of that current. We can see that this current would be going clockwise as seen from above, or it goes in the direction of that little red arrow there that says I. Now, we've done 4 steps. We first said, what is the direction of the current, of the existing magnetic field? We said, what is happening to the flux or the field? Sometimes the field can be constant, but because of the area is changing or something like that, because it's changing direction, you can have the flux decreasing or increasing. So we always have to ask ourselves, what is happening? What is the current direction of the field? And then what is happening to the flux? And then the third question was, what direction should an induced magnetic field go in order to oppose that change? And lastly, using the right-hand rule, for the magnetic fields produced by currents and loops, we need to figure out which direction the current is going to flow. Let's do the same thing for the second one. You have, again, the north is pointing up. So the magnetic field is still going in the same direction it was going. It's going up. But now the magnet is being pulled away from the loop. So the strength of the magnetic field is decreasing, which means the existing field direction is up, but it's going to be decreasing, which means an induced magnetic field should be such as to reinforce that field that we're losing. So we want our induced magnetic field to be pointing up. And what does that mean? Well, if you, just like it shows in the picture here, if you want your induced field to point up, your current has to flow counterclockwise. And so as you can see, that little red arrow there with the eye does indeed show the current going in a counterclockwise direction. Now let's do one more. And this one, in example C as it's shown here, you note that now the south end of the magnet is pointing towards the loop. Now, magnetic fields point towards south, so the direction of the existing magnetic field is down. It's going down towards the magnet, not up and away from it. So the existing magnetic field is pointing down, but it is getting stronger because we are bringing the magnet closer to the loop. You see the little arrow showing the velocity vector for the magnet shows it going up. So we have an existing field that points down. We have it increasing in strength. So therefore, according to Lenz's law, in order to oppose the change in flux, we need to have a field that points up. And how do you get a field that points up? Well, you have a counterclockwise current as seen from above in this picture here. So you can do the last one on your own. D is the last, well, D and E are the last ones to do, but look in E. In E there you got a magnetic field and you got a current loop, but the flux is not changing. So if the flux is not changing because the magnet is stationary, you'll notice that on the meter there's no current flowing. And that's why that's so. So we're going to do some example problems like this, but this is the basic four-step process you go through. You say, what direction is the existing field? How is it changing, or how is the flux changing? What induced magnetic field would oppose that change? And what direction of current flow would produce that induced magnetic field that you need to have to oppose the change?
Here's a nice numerical problem for you to work on. You have a 505 turn circular loop coil with a diameter of 15.5 centimeters and is initially aligned so the plane is perpendicular to the Earth's magnetic field. In 2.77 microseconds, the coil is rotated 90 degrees, so that is now parallel to the Earth's magnetic field. If an average EMF of 0.166 volts is induced in the coil, what is the value of the Earth's magnetic field? And does the induced magnetic field tend to add to or decrease the Earth's field? There, the answer is down there. So a couple of things to watch out for, and I'll let you work on this one on your own. Note that your diameter is given in centimeters, and it is a diameter. Since this is a circular loop coil, you're going to want to convert that diameter to the radius and then use your formula for the area of the radius. And then also note that you have 505 turns, so anything that you're going to do with one loop, you're going to have to multiply by 505 to get the total effect. And then they give you the time it takes for this field to go from essentially the plane of the loop is perpendicular to the Earth's magnetic field, so that means that the normal line to the coil is parallel to the Earth's magnetic field. So when you rotate it 90 degrees, it's actually going to be taking away from the Earth's magnetic field, so it's going to reduce to 0 in 2.77 milliseconds. So see if you can work it out and if you get the same answer as shown here. This problem embodies the idea of what we call an emotional EMF. So we have a rectangular coil of N loops, and they have a width A and a length B, and it is being pushed into a region where there's a uniform magnetic field of B. Now, if the coil is pushed with a speed V, what EMF will be induced in the coil? What direction will the induced current flow through the coil? Is it counterclockwise or clockwise? And it gives us a little hint there. Well, looking over at the right there, you see that you have a parameter x. And that x is supposed to be the amount of side B of your rectangular loop that is exposed to the magnetic field. And so the area of your loop that has magnetic field flowing through it is A times x. And so therefore A times x times big B would give us the magnetic flux that is flowing through your loop right now. But as you push it in, x is changing. And so the rate of change of your magnetic flux is the rate of change of A, which is a constant, times x, which is a variable, times big B. And if you take that derivative, you're left with A times big B times dx dt. But dx dt is a constant. It's saying we're pushing with a constant speed v. And so what you end up with is A times B, the magnetic field strength, times v, where v is the speed. And that's a general formula that you can use to figure out these motional EMFs. And that gives you the rate of change of flux, which should be equal to the EMF. And once you have the EMF, we need to figure out what direction it's going to flow. Well, currently the existing magnetic field is pointing into the plane of the paper, and it is increasing. So we are going to have a induced current that is going to produce a magnetic field that will be flowing out of the plane of the board so as to oppose the change in flux, which means that we should have a current that is going counterclockwise.